Welcome to The Explainer. Today, we are pulling back the curtain on one of the most fundamental ideas in all of computer science, data structures. They are the invisible skeleton that holds up our entire digital world, from the simplest app on your phone to the most massive global systems.
I mean, just think about it for a second. Your social media feed, a huge company database, the entire internet. At the end of the day, it's all just data. So how does a computer sift through these digital mountains to find that one specific thing you're looking for in, a fraction of a second? The answer isn't magic. It's just really smart engineering. It all comes down to the art and science of data structures. So let's dive in.
All right, before we get into the nitty-gritty, there's a key idea we got to get straight: the abstract data type, or ADT. Think of an ADT like an architect's blueprint. It just defines the what. It says, I want a thing that can store items, add new ones, and remove old ones. It doesn't care how you do it. The data structure, that's the actual building. It's the steel and concrete. It's the how. So let's explore some of these blueprints and the amazing things people have built with them.
To really get why this matters, we have to start with the most basic, most intuitive way you could possibly think of to store a bunch of stuff. This is our first shot at solving the problem, and our tool is the simple array. An array is just beautifully simple. Picture a long row of numbered boxes, all sitting right next to each other inside the computer's memory. This is what we call contiguous memory. If you want the item in box number 5, you just go straight to box number 5. No searching, no fuss. Access is incredibly fast. And you might be thinking, well, that sounds perfect. Why would we need anything else? Well, it's not quite that simple.
So here's the big catch. What happens when you need to stick a new item into an array that's already full? Let's say you want to add something at position 25. You can't just put it there. First, you have to take every single item after position 25 and painstakingly shift it one spot over to the right, just to make room. And only then can you finally place your new item.
Now, imagine you're not dealing with 50 items, but with 1 million or 100 million. All of that shifting takes real time, and for a user, that time feels like lag, the spinning wheel of death, and just plain frustration. If your data is changing all the time, an array's rigid nature becomes a huge performance killer. So, it's pretty clear. We need a more flexible way to do this. And that leads us right to our next big idea, the linked list. This whole structure was basically invented to fix the array's biggest problem by tossing out that everything must be neighbors rule. So instead of one big solid block of memory, a linked list is more like a chain. Each link in that chain, we call it a node, holds two things: the piece of data you actually care about, and a pointer, which is really just the memory address of the next node in the chain. These nodes can be scattered all over the place in memory. The pointers are what tie them all together in the right order.
Now, this elegantly solves our insertion and deletion problem. To get rid of an element, you don't have to shift a million other things. You just find the node before the one you want to remove, and you change its next pointer to simply skip over the unwanted node. It's like a quick surgical snip and retie. It's incredibly fast and efficient.
But remember the golden rule of data structures. There's always a cost, always a benefit. A trade-off. We got our fast insertions and deletions, but what did we give up? Fast access. See, with an array, you can jump to any box instantly. But with a linked list, if you want to find the 500th element, you've got no choice but to start at the very beginning and follow the chain, link by link, 499 times. That's a linear search, and for a big list, it is painfully slow.
So our quest isn't over. We want that flexibility we got from the linked list, but we desperately need the fast search speeds we gave up. And this pushes us to a totally new way of thinking about organization, moving from a straight line to a branching structure. Let's talk about the binary search tree, or BST.
So just to set the stage, imagine you've got 1 million items you need to search through. Let's see how our different data structures would handle a job that big.
And this, right here, is the jaw-dropping power of the BST. A linked list, in the worst-case scenario, might have to look at all 1 million items. A balanced binary search tree, on the other hand, finds what it's looking for in about 20 comparisons. Not 20,000, just 20. That is an absolute game changer. So, how is that even possible?
The magic is all in the organization. A BST is a tree of nodes that follows one simple but incredibly powerful rule. For any node you pick, everything in its left branch is smaller and everything in its right branch is bigger. So when you search, you start at the top and you ask one question. Is my target bigger or smaller than this node? If it's smaller, you go left. Bigger, you go right. With every single choice, you throw away half of the remaining data. It's basically the game 20 questions for your computer.
And building the tree uses that exact same logic. You take your new item, start at the root, and compare. Is it smaller? Go left. Larger? Go right. You just keep doing that, walking down the tree level by level, until you find an empty spot where the new node fits, perfectly preserving that sorted order for the entire tree.
Okay, so the binary search tree seems perfect, right? It's got fast search, and since it's just nodes and pointers, adding and removing stuff is also fast. So have we finally done it? Have we found the one perfect data structure? Well, unfortunately, no. Even the BST has an Achilles heel. What happens if you try to insert data that's already sorted? You don't get that nice, bushy, efficient tree. Instead, every new item just gets tacked onto the right side of the previous one, forming a long, pathetic, spindly chain. You've basically, accidentally, rebuilt a slow linked list, and all that amazing search speed is just gone. This is what we call a degenerate tree.
Now, of course, there's a solution to this. It's a more advanced version, like a self-balancing tree. These are really clever. They automatically perform these little operations called rotations to keep themselves from getting too spindly. They stay bushy and balanced no matter what order you throw data at them, which guarantees that super fast search time we were so excited about.
So far, we've really been focused on storing things and finding them later. But sometimes the problem isn't about finding data at all. It's about processing it in a very specific order. And for that, we need a whole different set of specialized tools. First up, we have the stack, and its principle is dead simple. Last in, first out, or LIFO. The very last thing you put in is the very first thing you can take out. The classic example is a stack of cafeteria trays. You push a new tray onto the top, and when you need one, you pop a tray right off the top. You never, ever take one from the middle.
And this isn't just some abstract idea. This is fundamental to how pretty much every program you've ever used actually runs. It's called the call stack. When one piece of your code calls another, the computer pushes its current location onto a stack. Then, when that other function is done, it pops that location off the stack so it knows exactly where to go back to. It's the computer's breadcrumb trail.
Now, the conceptual sibling of the stack is the queue, and it works on the exact opposite principle. First in, first out, or FIFO. This is just the line at the grocery store. The first person to get in line is the first person to get checked out. You add new people to the back of the line, and you serve people from the front. Simple as that.
But what if the line isn't just first come, first served? What if some people are more important? For that, we use a priority queue, which is often built using another structure called a heap. A heap is a special kind of tree with one rule. The highest priority item is always kept at the very top, at the root. That means it's always ready for instant removal, no matter how many other items are in there.
Finally, what if you need the absolute fastest lookup speed humanly possible? That's where hashing comes in. A special hash function does some math to convert your key, say the word apple, directly into an array index, like the number 4. You don't search at all, you just do a quick calculation and go straight to the right spot. It's what we call a constant time operation, and it's theoretically the fastest you can get. But you know the drill by now. There's always a trade-off. What happens if your hash function is a little imperfect and gives you the exact same index for 2 different keys? This is called a collision. A really common way to solve this is to just turn each slot in your array into a tiny little linked list. So if multiple items hash to the same spot, they just form a little chain there, which, hey, neatly ties back to one of the first structures we learned about.
So, after this whole journey, here's the final scorecard. Each structure shines in some areas and kind of struggles in others. The array gives you that instant access, but is a real pain to modify. The linked list is super flexible for changes, but painfully slow to search. A balanced tree? That offers a fantastic compromise, a real best-of-both-worlds solution. And the hash table gives us, on average, the holy grail of instant operations.
This just proves there is no single best data structure. The right choice depends completely on the problem you're trying to solve.
This really is the core lesson, isn't it? Every single choice is a trade-off. Choosing a data structure isn't about finding the one perfect tool. It's about understanding the cost you're willing to pay to get the benefits you absolutely need. Are you optimizing for speed when you read data or when you write data? Or maybe you're most concerned about how much memory you're using.
And this brings us to the ultimate point. The data structure isn't just a box to put things in. It's a tool for solving problems. A well-chosen, well-built structure can make a really complex problem feel simple, and an impossible-seeming problem suddenly possible. It can be the one thing that makes the difference between a program that flies and one that just crawls.
So the next time you use an app that feels unbelievably fast and responsive, or, one that lags and stutters every time you click, think about that invisible architecture working or not working underneath. The choice of data structure is shaping your entire digital experience. It is the skeleton that gives our software its shape, its strength, and its speed. Thanks for joining us on The Explainer.